Hello, everyone. My name is Xiangcheng. I'm now a postdoc at UC Berkeley. I was given this. I think it's on. Yeah. I was given this opportunity to talk literally last week, so I'm very glad to be here. This is the first attempt I tried to organize my talk in this point of view. It's using high redshift galaxies as a probe of testing feedback models in galaxy formation theory. What I mean by that is that this kind of viewing point is not widely discussed in the literature or in the community at this point. But high redshift galaxies is actually a very powerful way of testing feedback models in terms of high redshift galaxies probe a very different parameter space in galaxy formation than if you're only using low redshift galaxies or local galaxies. Also, we have more and more high good quality data in the next few years with JWST, ALMA, and etc. that can bring us a lot of data points to compare between model and observations. So I will talk about some of the work I have been doing with the cosmological zoom-in simulations using the FIRE ISM star formation feedback model and put it in context with other simulations in the literature and discuss what we agree and disagree and what data we will need in order to test these models in the next few years. So let's start with what I have been doing for the FIRE simulations is that we have been building this suite of high resolution cosmological zoom-in simulations of high redshift galaxies at redshift 5 and to 12. We cover 35 cosmological zoom-in regions, but we have over 1,000 halos in the broad mass range, and we have we push the resolution as far as we can. It's currently 100 to 7,000 solar masses for the baronic masses, and we have for softening about a quarter parsec or sub-parsec resolution. So we use the FIRE multiphase interstellar medium star formation feedback models, and we also compare with the extensive library we had for the whole FIRE collaboration at redshift 0 and redshift 2. So this is some pretty images. There are several papers we have been publishing in the past few years about these suite of high redshifts galaxy simulations. So, yes. Well, I think the best constraint we have for high redshift galaxies is the bright and UV luminosity function up to redshift 8. As Richard had been saying that different measurements actually agree with each other pretty well at this point. And all the simulations, all people doing simulations compare with the bright and UV luminosity function at this point. And they all claim they kind of agree, sort of agree, or something like that. I think we're doing pretty well for this kind of thing, but I think one of the first questions I want to bring about is the stellar mass-halo mass relation at this redshift and its evolution. So for the FIRE simulation, this is from my paper that we don't see very significant evolution from redshift 6 to redshift 10 on the stellar mass-halo mass relation. But if you look at it in the literature, different people claim very differently. They find positive evolution, negative evolution, no evolution at all, so on and so forth. So this is a very major point that we disagree for the modelers. And this problem needs to be solved in order to testing the feedback model we use. Some of the discrepancies come from like the stellar mass function measurement at this point is not great as well, because if you look at the very recent constraints, they discrete by over the order magnitude. So this is something we need to get better for using future data like JWST. Some of the other discrepancies on the stellar mass-halo mass relation may come from how to convert, how to do SCD feeding, and how to convert UV luminosity to a stellar mass, as well as how to assume the star formation efficiency in high redshift galaxies and something like that. So there are a lot of things we need to figure out in the next few years. So another prediction we have for the high redshift galaxy simulation we've been running is that we see the star formation is very bursty, or there's a large time variability in the star formation rate for the high redshift galaxies over a broad mass range. Even when the stellar mass is a few 10 to the 10 solar masses, the star formation rate is still going up and down on the time scale of tens to 100 million year time scale. So this is also something that other simulation has been pointing out, like the work done by Kim and Sen and Daniel Santorino and the Japanese group. You'll find this kind of bursty star formation. So another feature produced in the FIRE simulations is that we find star clusters in almost all the galaxies we have. So this is the 3 example galaxies in my sample from 10 to 10 to 10 to 12 in halo mass, but over 3 orders of magnitude in stellar mass. They all have these little blobs. Usually I call them like a rash or a skin disease of galaxies, but we want to look at this galaxy particularly in slightly greater detail. And this galaxy is actually this one. I will show a movie that's showing this starburst. Here, let's get it started. We see gas flows in and before the burst, and the galaxy builds up a large amount of gas reservoir, and the gas is highly turbulent and chaotic, and there are a lot of compressions in high density region. So if you look at just this one particular region that compressed by a lot of gas stream collision, you find this is the sweet spot for compact gravitationally bound star cluster to form. So if you look at the movie here, it's actually seeing different several cloud complex form compressed high pressure GMC, and star forms in this GMC at a rate of nearly 100% star formation efficiency, and it ends up with a bound star cluster. So keep going, the feedback starts to blow out super bubbles, and the super bubbles sweep up the rest part of SM, and the outflow is also compressing the gas in the ISM. So if you look at this point, this is another sweet spot for cluster formation. As you see, there's an outflow sweeping up the SM and compress this particular region of the interstellar medium and form a high pressure gas cloud, and stars form here and becomes a gravitationally bound star cluster. So we found in our simulations this is pretty common, and all the star cluster follows broadly like m to the -2 mass function. So all of these regions usually have very high gas surface density and high pressure. So just keep going about this, and the feedback blows out everything until it can temporarily suppress the star formation in the galaxy, and then eventually the gas will fall back again. So this is just the galaxy we were looking at. This is just to say that I think the whole picture is not that crazy. We find a lot of star clusters. This is a high redshift galaxy analog, HARO 11 in the local universe. It also has over 200 star clusters forming in this galaxy. And this is one of the cluster forming sites in the Milky Way, I suppose. And this is, by eye, it looks very like what we have in our simulations. I'm just trying to say this is not something crazy, I think. So the prediction is generally that in high redshift galaxies, the gas fraction is very high and the ISM is highly turbulent supported. You have a high chance of forming a high pressure region by cloud collision or feedback sweeping up the ISM during the compression. The consequence is that the ISM it's very chaotic, and there's no well-defined rotational support. There is no well-defined gas disk, and the stellar component is pretty clumpy because the galaxy is dominated by few star clusters. But if you look at other simulations in the literature, well, I should say some simulations do agree with our picture. They also find a highly turbulent ISM, etc. But for some other simulations that in the literature, as you can see, this is redshift 6, redshift 8, redshift 9. This is a simulation from Hardy Cates, and this is from the Italian group, I think. All these galaxies have a halo mass around the field 10 to the 11 or 1 point something 10 to 11, but the stellar mass they have, it's actually a factor of 3 larger than what we have in our simulations. But in all of these cases, they have a nice rotationally supported disk. So this is something we highly disagree between different models. I think that the reason for this discrepancy is the star formation feedback models implemented in these simulations. So this is something we have to figure out. So moving forward, I think the idea I want to convey in this talk is that high redshift galaxies can be used as a way to probe or testing feedback models in simulations. What do we disagree so far? One thing is the stellar mass halo mass relation and its evolution, and the other thing is that what is the ISM property, how stars form in high redshift galaxies, as well as the morphology and kinematics of these galaxies. Going forward, and what kind of observations do we want? Of course, better measurement on galaxy stellar masses is very important. Moreover, the morphology of high redshift galaxies, are they clumpy or compact or no feature at all? This is a very important constraint on the star formation feedback models. Also, there might be some ways to quantify the burstiness of star formation. Especially, it's very important in the high redshift and high mass end, because some people see bursty star formation, some people don't. This is a way of testing the ISM property. Probably the best way is using H alpha versus UV-derived star formation rate, but also Balmer break is probably another way of quantifying star formation history of these galaxies. So finally, we need gas kinematics. We need to know whether high redshift galaxies are turbulent supported or rotation supported, or a combination of both, and what fraction of them are rotation supported versus turbulent supported. So all of these investigations depend on feedback models in simulations. And there are state-of-art simulations that we want to study, for example, like Lyman alpha line profile, escape fraction of ions and photons, C2 emission, CO emission, even supermassive black hole growth. They all have to depend on the feedback model. This is very important to figure out in the next few years. So thank you very much. Yes.
So I think that in the way that we are treating random errors and perhaps systematics are very different between the different modelers.
Yes.
Especially in the empirical modelers.
Yeah.
I think most of the source is that we haven't agreed how to treat these random errors and the systematics. I think is also the part of the disagreement. And
yeah.
also how to compare the simulation directly with these empirical models and with observations and so that very easy.
Yeah. Frank?
I couldn't help but notice in just qualitatively from the images you showed, it did show clumpy turbulent X's, that in general all of those galaxies look incredibly smooth. Do you know if the modelers that are finding rotationally supported disks typically are doing simulations at lower resolution than the ones you use, either
Yeah. Yeah, my suspicions there. Yeah, my suspicions there are two things. First, they might not have the resolution to resolve individual giant molecular clouds in the simulations, and typically the feedback is also likely some kind of weaker than what we assume in our simulations, which gives a higher stellar mass in their simulations. If there is a higher stellar mass, they form a compact bulge in the center of the galaxy, and the bulge have a very deep gravitational potential that can hold the gas disk, and the gas disk can circularize before they can form stars. So I think that's why they have gas disks.
So you showed two results, one where you argue that there's no indication of large amounts of scatter in the stellar mass-halo mass relation.
Oh, no evolution, not scatter.
No evolution.
Yeah, no evolution.
But what about the scatter? How big is the scatter at the low mass end of your probe? 10 to the 10 solar mass.
Yeah, what we usually have is like 0.5 dex.
0.5.
Yeah.
Okay, and
I'm just going to ask a question more about the conclusion that the star formation rates are bursty
Yeah.
in the galaxies. I mean, obviously we need things like H alpha and UV to help differentiate those. When you look at the simulations over, say, the time scale you would be able to measure these star formation rates, would you conclude they're bursty if you could look at the UV, for example, or do you really need the H alpha?
Yeah, I think if UV probe a longer time scale, it's the variation is of that time scale. So if it's H alpha derived as SFR, the burstiness is of time scale like below 10 million years or even 10 to 50 million years. But if you look at UV alone, it's probably of order 100 million year.
Right,
So
so
the burstiness.
When you say bursty, over what time scale are you referring to?
I think it's of the same order as the dynamic time scale of the galaxy. It's usually of order 20 to 50 mega years. You can see the cycle, the whole cycle, right?
Something to the Chen's prerogative. I think this is probably a naive question. I'm a low redshift person, but how much? Oh, there's no time. No, sorry. How much can you tell from luminosity function alone in different bands in terms of burstiness? Because presumably the galaxies are drifting in and out of different bands in a luminosity function.
Yeah, I think that's a very good question because different bands also provide a probe of the stellar mass function, and because people can measure stellar mass from different bands. So I think that would definitely help.
Okay.
I have to start more careful about how to quantify that.
Yeah, great.
Yeah. I'm only here for today and Thursday, so if you have any question, please grab me as soon as possible.
So let's thank Xiangcheng again.
Do you mind?